On July 12, 2022, NASA released the first full-color images from the James Webb Space Telescope, and the universe suddenly looked older, stranger, and far more crowded than anyone had promised. The first deep field focused on a cluster called SMACSO 723, revealed thousands of galaxies smeared across a patch of sky no wider than a grain of sand held at arm's length. But it was not the beauty that stopped astronomers cold, it was the arithmetic. Within weeks, teams poring over Webb's infrared data began flagging faint red smudges that carried an impossible signature. These were galaxies whose light had traveled for more than 13 billion years, dating to a time when the cosmos was only a few 100 million years old. According to the standard timeline, that era should have held little more than gas, darkness, and the faintest first stars. Instead, Webb showed objects that were bright, compact, and disturbingly well-formed. Some appeared to shine with the output of tens of billions of suns. A few looked as though they had already assembled the stellar mass of a mature galaxy, the kind of structure that ordinarily takes billions of years to build. The Big Bang model, refined across decades and confirmed by the cosmic microwave background, predicted a slow, gradual assembly. First atoms, then dark clumps, then the slow gravitational pull that gathered gas into the earliest stars around 100 to 200 million years after the beginning. Galaxies were supposed to grow patiently, merging and swelling over cosmic time. Yet here were candidates that seemed to skip the waiting. They were labeled with cryptic designations and cataloged with cautious question marks, but the pattern repeated across multiple independent fields. The same too bright, too early problems surfaced again and again. Astronomers had built Webb precisely to see this frontier, the first few 100 million years no telescope had ever resolved. They expected surprises. They did not expect the surprises to look like a contradiction. To understand why a smear of infrared light could rattle the foundations of cosmology, we first have to understand the machine that captured it, and the strange physics that lets a telescope read time itself. The James Webb Space Telescope is not aimed at distant places so much as distant times. Every telescope is a time machine, because light travels at a fixed speed, and the farther away an object sits, the older the light that finally reaches us. Webb was engineered to push that principle to its limit. Its primary mirror spans 6.5 meters, built from 18 hexagonal segments coated in a microscopically thin layer of gold, giving it more than 6 times the light-gathering area of Hubble. That size matters, because the galaxies from the first few 100 million years are staggeringly faint. But size alone was not enough. The real breakthrough was infrared. As the universe expands, it stretches the light traveling through it. Ultraviolet and visible light, emitted by young, hot stars in the early cosmos, gets dragged toward longer, redder wavelengths. A shift so extreme that after 13 billion years, that light arrives as infrared. Hubble, tuned mostly to visible wavelengths, was partly blind to this era. Webb was built to hunt it. Its instruments, NIR-CAM and NIR-SPEC, capture the faint infrared glow and split it into spectra, revealing the fingerprints of hydrogen, oxygen, and carbon. To detect such feeble heat, the telescope must be brutally cold. It sits about 1.5 million kilometers from Earth, at the second Lagrange point, shielded by a 5-layer sunshield the size of a tennis court that drops its instruments to around minus 233 degrees Celsius. The key measurement is redshift, written as Z. A galaxy at redshift 14 existed when the universe was roughly 290 million years old. The higher the Z, the deeper into the past, and the closer to the Big Bang itself. Webb reads that number by measuring exactly how far the light has been stretched, converting a color shift into a cosmic clock reading. This is how astronomers date a smudge of infrared to the dawn of everything. And when they turn that clock on one particular object, a galaxy cataloged in the JADE survey, the reading came back at a value that made the whole team look twice. The object is called JADE's GSZ 140, and its name encodes its story. JADE stands for the JWST Advanced Deep Extragalactic Survey, one of the telescope's flagship programs. GS marks the field, the good south region of sky. And Z14 is the crucial part, a redshift of about 14.32, the highest confirmed at the time of its announcement in 2024. That number translates into a specific moment. The light from this galaxy left it when the universe was roughly 290 million years old, barely 2% of its current age. When astronomers confirmed the redshift with NIR spectroscopy, capturing the telltale break in its spectrum, they knew they were looking at one of the earliest galaxies humanity has ever seen. What made it extraordinary was not merely its distance, but its character. JADE's GSZ140 is bright, far brighter than models comfortably allowed for so young a universe. Its light spreads across a region estimated at about 1/600 light-years, meaning this is not a single point-like burst, but an extended structure with real size. That extension told astronomers the glow came overwhelmingly from stars, not from a single compact source. Estimates suggested it had already assembled hundreds of millions of solar masses of stars, and the presence of oxygen detected in follow-up observations hinted at chemical enrichment, the residue of earlier generations of stars that had already lived and died. This is the puzzle. Enriching a galaxy with oxygen requires stars to form, burn, and explode as supernovae, seeding heavier elements into the surrounding gas. That is a multi-step process. Yet here it appeared to have happened in under 300 million years, a cosmic instant. The galaxy looked too developed, too luminous, and too chemically mature for its age. It behaved less like a newborn and more like a precocious adolescent that had skipped its childhood entirely. JADE's GSZ140 was not alone. It was the sharpest example of a broader pattern Webb kept finding at high redshift. And when researchers tried to calculate just how much mass these early galaxies contained, the first numbers that came back would ignite a genuine crisis. In early 2023, a team led by astronomer Ivo Labe published a result that sent a jolt through the field. Using Webb's earliest CEERS survey data, they identified 6 candidate galaxies from roughly 500 to 700 million years after the Big Bang that appeared shockingly massive. The brightness of these objects, converted into stellar mass using standard assumptions, implied that some held tens of billions of solar masses of stars. One candidate appeared to contain as much as 100 billion solar masses, a figure comparable to the modern Milky Way, packed into a galaxy that existed when the universe was less than a 20th of its present age. That was the collision point with theory. Standard cosmology, built on the lambda-cold dark matter model, sets a hard limit on how much matter could have gathered so early. In the first few 100 million years, only so many dark matter halos could have grown, and each halo can trap only a finite amount of ordinary gas, roughly 16% of its total mass, matching the cosmic ratio of normal matter to dark matter. Even if a galaxy converted every single atom of available gas into stars with perfect 100% efficiency, there simply should not have been enough raw material to build 100 billion solar masses that fast. Real galaxies are far less efficient, typically turning only a few percent of their gas into stars. The observed masses seem to demand efficiencies of near totality, or halos far larger than the young universe could have produced. Either the measurements were wrong, or the model was. Researchers were careful. These were photometric estimates, derived from brightness across a handful of filters rather than full spectra, and everyone acknowledged the uncertainty. But the numbers were startling enough to publish, and startling enough to name the tension openly. If confirmed, these galaxies would strain the standard timeline of cosmic structure formation to its breaking point. The scientific community reacted with measured caution, demanding spectra and independent checks. The wider world reacted very differently. Within days, the story escaped the journals, and the headlines began to announce that Webb had broken the universe. The transformation from cautious paper to cultural earthquake took almost no time at all. By February 2023, articles and viral posts declared that the James Webb Space Telescope had disproven the Big Bang. Headlines announced that cosmology was in crisis, that the Standard Model had collapsed, that everything astronomers thought they knew about the universe was wrong. Some commentators, a few with credentials and many without, seized the moment to promote alternative theories, from tired light models to steady-state revivals, insisting that Webb had vindicated ideas mainstream science had discarded decades earlier. The reality inside observatories looked nothing like that. The scientists who had actually flagged the massive galaxy candidates were among the most cautious voices in the room. Ivo Lebey and his colleagues had explicitly written that their masses were preliminary, dependent on assumptions that follow-up observations could overturn. They asked for spectroscopy, the gold standard that would confirm the true distances and the true nature of the light. They did not claim the Big Bang was dead. They claimed there was a tension worth investigating, which is exactly what science is supposed to do. This gap between headline and laboratory is a recurring feature of modern astronomy. The Big Bang model does not rest on a handful of galaxies. It stands on the cosmic microwave background, the leftover radiation from 380,000 years after the beginning, mapped in exquisite detail by the COBE, WMAP, and Planck missions. It stands on the measured abundances of hydrogen, helium, and lithium forged in the first minutes. It stands on the expansion of space itself, observed for nearly a century. A few overweight-looking galaxies could force refinements to models of star and galaxy formation, but they could not erase that mountain of independent evidence. Working astronomers understood this, and they responded methodically, not with panic but with data requests. They began pulling spectra, re-examining calibrations, and questioning the assumptions baked into those first mass estimates. The most important question was deceptively simple. What if the light was not coming only from stars? What if something far more compact, far more violent, was hiding inside these galaxies and inflating their apparent brightness? Before rewriting cosmology, astronomers asked a simpler question. What if some of that light never came from stars at all? At the center of many galaxies lurks a supermassive black hole, and when such a monster feeds, it becomes an active galactic nucleus, blazing across the spectrum. A disk of superheated gas spirals inward, reaching temperatures of millions of degrees, radiating with the intensity of trillions of suns. From billions of light years away, that pinpoint of accretion can masquerade as an entire population of ancient stars. This mattered enormously for the record breakers of 2022 and 2023. When teams first estimated stellar masses, they assumed nearly all the observed brightness traced starlight. But if a hidden black hole contributed a large fraction of the glow, then far fewer stars were needed to explain the same luminosity. The apparent contradictions shrank. A galaxy that seemed to hold 200 billion solar masses of stars might, in reality, hold only a tenth of that. Its excess brightness powered by a compact engine no wider than our solar system. Spectroscopy provided the crucial test. Instruments like Webb's NIR-SPEC dissected incoming light into fine wavelengths, hunting for the telltale signatures of accreting gas, broadened emission lines from hydrogen moving at thousands of kilometers per second, and high ionization features that starlight alone cannot produce. In several targets, including candidates once flagged as impossibly massive, astronomers found exactly those fingerprints. The objects were not overgrown stellar cities. They were early quasars, or hybrids, their central black holes surprisingly large for such young epochs. This reinterpretation dissolved some of the most alarming numbers. Galaxies that had triggered headlines about broken physics were quietly reclassified, their masses revised sharply downward. The universe, it turned out, had not necessarily built stars at an impossible rate. It had built black holes early and fed them hard. Yet the black hole explanation could not account for everything. Many bright sources showed no strong signs of an active nucleus. Their light looked stellar, their spectra clean. For those, a different correction was required. one that reached into the very equations used to convert brightness into mass. The next fix came not from black holes, but from the assumptions astronomers had made about the stars themselves. Turning a smudge of infrared light into a stellar mass requires a chain of assumptions, and in 2022, several links in that chain were weaker than anyone liked. The first was the initial mass function, the recipe describing how many small stars form for every giant. Standard models were calibrated on the modern Milky Way, but the early universe was different, hotter, denser, poorer in heavy elements. If those first galaxies produced proportionally more massive, luminous stars, then their brightness came from fewer objects, and their calculated masses had been badly overestimated. A galaxy could shine like a giant while weighing far less. Dust was the second correction. Interstellar dust absorbs starlight and re-emits it in the infrared, distorting a galaxy's apparent color and energy. Early estimates often assumed simple, local dust laws. Reanalysis with more flexible models allowed some of the observed glow to be redistributed, again lowering the required number of stars. Calibration itself was the third problem. Webb was a brand new instrument. In its first months, the conversion between raw detector counts and true brightness was still being refined. As the calibration matured through 2023, some measured fluxes shifted by tens of %, and the extreme outliers moved back toward expectation. Then came the emission lines. In young, furiously star-forming galaxies, glowing gas can contribute enormous brightness in narrow wavelength bands. When those lines fall inside a photometric filter, they can trick broadband measurements into reporting far more starlight than exists. Spectroscopy separated the gas from the stars and trimmed the estimates further. One by one, the corrections accumulated. Masses that had seemed to demand hundreds of billions of solar masses were revised down by factors of 3, 5, sometimes 10. Papers that once described a crisis were followed by papers describing resolution. The methodical machinery of science ground through the numbers, and much of the panic evaporated. Standard cosmology, the astronomers concluded, was not broken. It had been stressed by rushed measurements and optimistic assumptions, then relieved by patience. And yet, when every reasonable correction had been applied, a stubborn residue remained. Some galaxies were still too bright, too early, too fast. Those survivors are where the real mystery begins. Strip away the hidden black holes. Adjust the initial mass function. Fix the dust. Recalibrate the detectors. Subtract the glowing gas. Do all of it honestly, and a genuine puzzle refuses to disappear. A real population of unusually bright galaxies survives from the universe's first 500 million years, more numerous and more luminous than most pre-Webb models predicted. Jade's GSZ 14-0, seen just 290 million years after the Big Bang, is the clearest witness. Even under conservative assumptions, it is intrinsically bright and physically extended, hundreds of light-years across, with a stellar mass of hundreds of millions of suns. Spectroscopy shows no dominant black hole, no easy shortcut. Its light appears to come from stars, and those stars had to assemble astonishingly fast. The core problem is efficiency. In standard theory, only a modest fraction of a galaxy's available gas converts into stars before feedback, radiation, supernovae, and stellar winds blow the rest away and choke off growth. To explain the brightest early galaxies, that efficiency must be pushed unusually high, with a large share of gas turning into stars before the breaks engage. Several explanations compete. Perhaps feedback was weaker or slower in the early universe, letting star formation run unchecked in dense pockets. Perhaps the first stars were more massive and more luminous, producing dazzling light per unit mass. Perhaps star formation came in violent, bursty episodes, so that we catch these galaxies precisely during their brightest flare-ups, a selection effect that biases what Webb sees. Each idea solves part of the tension and strains against other observations. None yet commands consensus. What makes the puzzle durable is its statistics. This is not one anomalous object that might be a fluke or a misidentification. Survey after survey, from JADES to CEERS, keeps finding more of these luminous early systems than the simplest models allow. The abundance itself is the anomaly. So the crisis has changed shape. It is no longer a threat to the Big Bang, but a genuine, well-defined problem in astrophysics. How did the first galaxies grow so bright, so quickly, in so little time? The answer will not overturn cosmology. It will refine the story of how the first light emerged from darkness. So where does that leave us? The Big Bang stands unshaken. Every genuine test, the cosmic microwave background mapped by Planck, the abundance of primordial hydrogen and helium, the accelerating expansion measured across billions of light years, still points to a universe that began hot, dense, and roughly 13.8 billion years ago. Webb did not break that framework. It stress-tested it, and the foundation held. What Webb did break was our complacency about the details. The headlines of 2022 and 2023 were wrong about cosmology, but right about surprise. Astronomers genuinely did not expect galaxies this bright, this early, in this abundance. The corrections that followed, hidden black holes, revised stellar recipes, better calibration, dissolved the false crisis. But they could not erase the real one. A population of luminous early galaxies remains, and it demands that we rewrite the chapter on how the first stars ignited and how the first galaxies assembled. This is how science is supposed to work. Not a single triumphant answer, but a moving frontier, where a new instrument reveals what the old ones could not, and theory hurries to catch up. Models of feedback, of gas cooling, of the earliest stellar masses are being rebuilt right now, tuned against fresh spectra arriving month after month. The next generation of simulations must produce galaxies that shine as brightly as the ones Webb keeps finding. Future observations will sharpen the picture further. Deeper surveys will count these early galaxies precisely. Longer spectroscopic stares will weigh their stars and hunt for their black holes. Somewhere in that data lies the mechanism, the reason the cosmic dawn burned brighter and faster than our equations foretold. JADES GSZ 14-0 is not an error to be explained away. It is a signpost, a beam of ancient light telling us that the universe's opening act was more energetic, more efficient, more hurried than we imagined. The telescope did its job. Now theory must do its own, because the lesson of these first galaxies is neither confusion nor catastrophe, but humility, written in starlight from the edge of time. The cosmic dawn outpaced our models.